Here are the top 10 things you need to know about limits. Must know number 1. Calculating limits from a graph. Let's start with an informal definition of what a limit is. Some finite value L is the limit of f at x as x approaches a, if, as x gets closer and closer to a, f at x gets closer and closer to L. And we can describe that in limit notation by writing the limit of f at x as the x value approaches a is equal to L. And how you should be interpreting this notation is that the y values of the function are approaching L as the x values of the function are approaching a. And that limit at L only exists if the y values of the function are approaching L from both the left and right sides of a. And there's a notation for those one-sided limits, where this little minus sign means that x is approaching a from the left of a, and this little plus sign means x is approaching a from the right side of a. So if the y values of the function are approaching L, as x approaches a from both the left and right side, then the overall limit of f at x as x approaches a is equal to L. And the best way for me to help you understand what this all means is by calculating a limit of this piecewise function using its graph. I'll also write its equation above. It's made up of this linear function when x is less than 1. It's made up of this square root function when x is bigger than 1. And it's equal to this point right here when x is equal to 1. What we're going to do for this example is calculate this function's limit as x approaches 1. But that can only be calculated by first analyzing the function's limit as x approaches 1 from both the right side of 1 and the left side of 1. And since for all these limit calculations x is always approaching 1, I'm going to draw a vertical line through x equals 1 so we can see what the function needs to be approaching. Starting with this right-hand limit, we want to know, as the function approaches that blue line from the right of the blue line, what are the y values of the function getting closer and closer to? It might be easy for you to visualize that if I plot a point on the function that's to the right of x equals 1. That point has an x value and a y value. If you were to imagine this point moving closer and closer and closer to that blue line, the point's x value would be approaching 1 from the right side of 1, but what is its y value approaching? Well, it looks like the function is approaching this hole right here, and the y value of that hole is 2. So we could conclude that the limit of the y values of the function as x approaches 1 from the right side of 1 is equal to 2. But what about the left-hand limit? Starting to the left of x equals 1, as the function moves closer and closer and closer to having an x value of 1, what are its y values getting close to? Well, it looks like the function is approaching this hole right here, which has a y value of 0. So the limit of the y values of the function as x approaches 1 from the left is equal to 0. And since the right and left limits are not equal to each other, I know the limit of f at x as x approaches 1 does not exist, because limits only exist if the left and right limits are equal to each other. So I could say the overall limit does not exist. Now this example is good at highlighting an important property about limits. When calculating a limit as x approaches 1, we don't actually care where the function is when x is equal to 1. Right? The function when x equals 1 actually exists. It's right there at that point. We don't care where it is when x equals 1. We just want to know what is the function approaching as x approaches 1. So as this function is approaching 1 from the right and from the left, it's actually going towards 2 different y values, which is why even though the function exists when x equals 1, the limit does not exist as x is approaching 1. Must know number 2. How to calculate limits from an equation. In section 1, we calculated limits from a graph. Now let me show you a flowchart that is going to help you understand how we can calculate limits from an equation. Let's say we wanted to calculate the limit of f at x as x approaches a. The first thing that you will always try to do is direct substitution. And what that means is to just take the value that x is approaching and sub it in for x into your function and see what answer you get. One of three things is going to happen. If the function is continuous at the x value of a, then when you do direct substitution, you're going to get f at a is equal to some number. And when that happens, you've found your limit. The limit of f at x as x approaches a is equal to f at a. And just as a quick demonstration of that, if we have some continuous function, finding the limit of a function as it approaches any x value of a on a continuous function, we would find that as the function approaches the x value of a from the right and from the left, it's just approaching the actual point that is on the function. And that's all this says right here. But direct substitution is not always going to work. If the function is discontinuous at x equals a, two different things could happen. When you do direct substitution and try and evaluate f at a, you could get 0 over 0, which is an undefined expression that when dealing with limits, we call indeterminate form. And we call it indeterminate form because it doesn't tell us if the limit exists or not. You would have to try one of a few different strategies to try and rewrite the limit to be able to calculate its value. Different strategies you could try are factoring, multiplying by a conjugate, using a trig identity, or using L'Hopital's rule. The other thing that could happen if the function is discontinuous at x equals a is that when you do direct substitution, you calculate that f at a is equal some non-zero number over 0. And this actually means that the limit does not exist. And it actually usually means that there is a vertical asymptote at x equals a. But to verify if in fact it does have a vertical asymptote there, you would have to check the one-sided limits to check its behavior as x approaches a. Now we'll look more in depth at these two options in a couple future sections of this video. But in this section, let's do one example of a function that's continuous at x equals a, and we're able to calculate its limit very easily just using direct substitution. So let me make some room for that. Let's do an example where we find the limit of this function x squared minus 4 as x approaches 1. If I want to calculate that limit, I'll start by doing direct substitution. Just sub this x value into our function for x. So I would just have 1 squared minus 4, which is negative 3. And that's it. Since we were able to get a value when we did direct substitution, that's the value of the limit. Let me show you graphically what we just figured out. The function x squared minus 4 looks something like this. And I know the point 1, negative 3 is on the function. And I can see that as the function approaches this x value of 1, from both the left side of 1 and the right side of 1, the function is approaching this point that is on the function, the point that has a y value of negative 3. And we calculated that right here. So that's the value of the limit of x squared minus 4 as x approaches 1. Must know number 3, infinite limits. In this section, we'll look more carefully at what if the value of f at a equals some non-zero number over 0. This expression is undefined and actually indicates that the limit of f at x as x approaches a does not exist. And also, it usually indicates that there's a vertical asymptote at x equals a. But to know for sure if there's a vertical asymptote at x equals a, you have to check both the left and right-hand limits. If the limit as x approaches a from the left or from the right of f at x is equal to either plus or minus infinity, then that means there is a vertical asymptote at x equals a. And I should also clarify, a left or right-hand limit being equal to positive or negative infinity does not mean that the limit exists. It's just a way of describing the behavior of the function as x approaches a from the left and right. The limit as x approaches a still does not exist. And now let's do an example to see how this all works. So I'll make a bit of room, and we'll do this example. Let's find the limit of this rational function as x approaches negative 3. I would start by trying direct substitution by subbing negative 3 in for the x values in the function to see if it's continuous at that x value. So when I do direct substitution, I end up getting negative 6 plus 5, which is negative 1, being divided by 0. This expression is undefined, and because it's a non-zero number being divided by 0, I know that the limit does not exist. And when this happens, it's good to use a table of values to find the left and right limits so that you know the function's behavior as it approaches this x value of -3. So I'll make an xy table, and in this table, I'm going to put the x value of -3 in the middle of the table, and then choose x values that approach -3 from the left and from the right. And then for each of these x values, I'll use my function to calculate its corresponding value of y. Now let's focus in on when x is -3. The function doesn't exist, we know that, it's undefined. But as the x values of the function approach -3 from the left side of -3, notice that the y values start to get bigger and bigger and bigger. They seem to be going towards infinity. I could communicate that by saying that the limit of the function, as x approaches -3 from the left side of -3, is equal to infinity. Now, this doesn't mean that the limit exists. In fact, it verifies that the limit does not exist. Because for a limit to exist, it has to be trending towards some finite value, and infinity is not a finite value. But because we got that infinite limit, it does verify that there is a vertical asymptote at x equals -3. And let's also write down the right-hand limit. As the x values approach -3 from the right of -3, the y values seem to be trending towards -infinity. So the limit of our function, as x approaches -3 from the right side of -3, is equal to -infinity. And I'll draw a quick sketch of this graph just so you can visualize this. There's a vertical asymptote at x equals -3. There's a horizontal asymptote at y equals 2. And this function will be split into two branches. The branch to the left of x equals -3, I know as I approach -3 from the left, the function should be going up towards infinity, which means the function would look like this. And as I approach -3 from the right, the function has to go down towards -infinity, meaning it looks like this. Must know number 4. Indeterminate form of type 0/0. If the value of a function at a is equal to the undefined expression 0 divided by 0, then the limit of f at x as x approaches that a value might exist or it might not. So when evaluating a limit, if we do direct substitution and get this format 0/0, we call that indeterminate form because it doesn't allow us to determine if the limit exists or not. So what you have to do is try and rewrite that f at x function in a different but equivalent way so that you can evaluate the limit. And why we're allowed to try and rewrite the function before evaluating the limit is because of the rule that tells us if f at x is equal to g of x when x does not equal a, then the limits of both f at x and g of x as x approaches a are equal to each other. So what this rule is saying, if we have two functions that are equal to each other at all x values, except not necessarily at the x value of a, then the limits of those functions as x approaches a is going to be equal. Because for a limit, when x is just approaching a, we know x is never actually going to equal a, it's just getting closer and closer to a. So we wouldn't actually care if the functions were equal to each other when x was equal to a, we just want to make sure they're equal to each other at all other x values. Now, let me make a little bit of room and then introduce you to 3 strategies that make use of this rule: factoring, multiplying by a conjugate, and applying a trig identity. Let's start with example 1. If I zoom in on this example, we want to find the limit of this function as x approaches 5. When evaluating a limit, you always start by doing direct substitution. So when I sub this 5 in for all of my x values, I get 0 divided by 0, which is indeterminate form. So I don't know if this limit exists yet. I'll erase this direct substitution and try and simplify this function into an equivalent way that maybe I'll be able to evaluate the limit. I notice that the numerator can factor. It's a 3-term quadratic, so I find numbers that multiply to 10 and add to -7. The numbers that work are -5 and -2. So it would factor to x minus 5 times x minus 2. And now I have a factor of x minus 5 divided by a factor of x minus 5, which is 1, so I can cancel those factors. And what I'm left with is just this x minus 2 function. Now, being able to rewrite this limit in this format is because of the rule that we have right up here. These functions are equal to each other at all x values except for the x value of 5. The x value of 5 makes this expression undefined, but not that one. But since we're finding the limit as x is approaching 5, as long as these functions are equal at all x values except for 5, I know that their limits are going to be equal to each other. And now to find the limit of x minus 2 as x approaches 5, now direct substitution would work perfectly fine. I can sub in 5 for x, and I figure out that the limit as x approaches 5 is 3. Now let's try another example where we'll use a different strategy called multiplying by the conjugate. In this example, we want to find the limit of this function as x approaches 9. Always start with direct substitution. If I do that, I would get the undefined expression 0 divided by 0, which we call indeterminate form. So I can try and get this function out of indeterminate form and then retry evaluating the limit. I'll erase this direct substitution I did, and what I'm actually going to do is I'm going to multiply this function by 1 in a tricky way. I'm going to multiply top and bottom of it by root x plus 3. Before I simplify this multiplication, notice two things. First of all, we're just multiplying by 1. Something divided by itself is 1, so we're not changing the value of this function. But also notice how I chose the expression that's in the top and bottom of that fraction. It's the exact same as this expression, except the signs are opposite. So the product of these two expressions that are in the denominator is now a difference of squares. I'll rewrite the limit, and in the numerator I just have a product of x minus 9 and root x plus 3. I'll just write them beside each other. And in the denominator I have a root x minus 3 times a root x plus 3. That's a difference of squares. So following the difference of squares rule, that would be the square root of x squared minus a 3 squared. Root x squared is just x, and 3 squared is 9. And now notice there's a factor of x minus 9 being divided by itself. That's 1, so I can cancel those factors out. And I'm left with finding the limit as x approaches 9 of the function the square root of x plus 3. Now this function is equal to this function for all x values except for the x value of 9. That's okay because we're finding the limit as x approaches 9, which means the limits of these functions are going to be equal to each other. So I can try direct substitution again by subbing this 9 in for x, and I get root 9 plus 3, which is 6. And now let's move on to the last strategy I want to show you in this section, using a trig identity. So our third example, we need to find the limit of this function as x approaches 0. If I try direct substitution by subbing in 0 for x, I get sine of 0 divided by sine of 0. And sine of 0 is 0, so I get 0 over 0, which is indeterminate form. Which means I need to erase my direct substitution and try and rewrite this function in a way where I can evaluate the limit. Well, I know the double angle identity for sine tells me that sine of 2x is equal to 2 times sine x times cos x. So I'll replace it with that identity. These factors of sine can cancel, and then the limit of this function would be equal to the limit of the function with the signs canceled. And now I'll do direct substitution, and cosine of 0 is equal to 1. So I just have 1 over 2 as the value of my limit. Must know number 5, limit laws. I want to show you 4 laws that we've already been using some of them somewhat in the previous sections, but we'll continue using them for the rest of the video as well. The first law is the limit of a sum of functions. I know that would be equal to the sum of the limits. So the limit as x approaches a of f at x plus or minus g of x would be equal to the limit as x approaches a of f at x plus or minus the limit as x approaches a of g of x. The second rule is if we have the limit of a constant times a function. What we can do in that scenario is just do that constant times the limit as x approaches a of that function. The third rule is if we have a limit of a product of functions. That would be equal to just the product of the limits. And the last rule is if we have the limit of a quotient of functions. That would just be equal to the quotient of the limits, which means the limit of the function in the numerator divided by the limit of the function in the denominator. And now that you know those limit laws, we'll put them to good use throughout the video. Must-know number 6. Calculating limits at infinity. In this section, we'll be looking at how to calculate the limit of a function as its x values approach either positive or negative infinity. When we do this, we're essentially analyzing the behavior of a function as x gets very large in the positive or negative direction. And that will help us actually see if a function has a horizontal asymptote, because a line y equals b is a horizontal asymptote of f at x if the limit of the function as x approaches either positive infinity or negative infinity is equal to b. So let me show you an example of how we could calculate a limit at infinity. In this example, I want the limit of this function as x approaches infinity. When trying to evaluate the limit of this function, I can see that as x approaches infinity, both the numerator and denominator would be approaching infinity, which would give me the indeterminate form of type infinity over infinity. When that happens, we'll erase that, and we'll use a little trick to evaluate the limit. You can find the highest power of x that's in the denominator, in this case, that's an x squared, and you can divide all of the terms in this function by that highest power of x. Algebraically, what's actually happening is you would just be multiplying top and bottom of this function by 1 over x squared. Right, something divided by itself is 1, so we're just multiplying by 1, which doesn't change this function's value. It's just going to get it into a different format where we'll be able to evaluate the limit. So as I simplify this, all three terms in the numerator are getting multiplied by 1 over x squared, and both of the terms in the denominator are also getting multiplied by 1 over x squared, which accomplishes what we want to do. We want to divide all the terms by this highest power of x that's in the denominator. And when I do that, this first term being divided by x squared just becomes 5. This term becomes 8 over x, and this term becomes negative 3 over x squared. And then in the denominator, 3x squared divided by x squared is 3, and 2 divided by the x squared becomes just 2 over x squared. And now using the limit laws I taught you in the last section, to find the limit of this whole function, I can just look at the limit of each of these individual terms as x goes to infinity. Well, as x goes to infinity, 5 and 3 are constant values, so they remain unchanged. But each of these terms, where there's a constant in the numerator, and then an x in the denominator, as x goes to infinity, each of these denominators are going to infinity, which makes the values of each of those fractions start getting closer and closer to 0. So that leaves me with my limit being 5 plus 0 minus 0 over 3 plus 0. And of course, that would simplify to just 5 over 3. And because this infinite limit equals this finite value 5/3, I know the graph of this function would have a horizontal asymptote at 5/3. Let me show you what that graph would look like roughly. Now this is just a rough sketch, but you can see that as x approaches both negative infinity and positive infinity, the y values of the function seem to be approaching this horizontal line, its horizontal asymptote, y equals 5/3. Must know number 7, L'Hopital's rule. If when you are evaluating a limit, you get an indeterminate form of type 0 over 0 or infinity over infinity, you can use L'Hopital's rule, which states that the limit of a quotient of two functions as x approaches c would be equal to the limit as x approaches c of the derivative of the function that's in the numerator divided by the derivative of the function that's in the denominator. So let's look at two examples of how we could use this rule. Let's start with example 1. The first thing you should always do when trying to evaluate a limit is to try direct substitution. Let's sub into this function and see what it equals. When subbing in 2, I get 0 over 0, which is an undefined expression that we call indeterminate form. When that happens, there's a couple different things you can try to rewrite the function. In a previous section, I told you that you could try factoring and simplifying that expression. And if we did that, I would be able to cancel these factors of x minus 2, and then find the limit as x approaches 2 of this simplified function, which would just be 2 minus 5, which equals negative 3. But what we can do in this section, when we have that indeterminate form of type 0 over 0, instead of doing that factoring and simplifying, we can use L'Hopital's rule. I could find the limit as x approaches 2 of the derivative of the top divided by the derivative of the bottom. So let me differentiate both the numerator and denominator of this function. So I'm finding the limit as x approaches 2 of the derivative of the top, which would just be 2x minus 7, divided by the derivative of the function in the bottom. The derivative of that function is just 1. And now if I try direct substitution by subbing in this 2 for x, I get that answer of -3 that I showed you earlier is what we should get for the limit of that function. Let's now try example 2. Let's find the limit of this function as x approaches infinity. Well, in the last section, I showed you there is a trick for evaluating infinite limits. You just have to divide all of the terms in the function by the highest power of x that's in the denominator. So we'd multiply top and bottom of this by 1 over x squared. But instead of doing that, I noticed that if x is going to infinity, both the numerator and denominator of this function are both going to infinity. So this would give me indeterminate form of type infinity over infinity. And when you get that indeterminate form, you're allowed to use L'Hopital's rule. And to use L'Hopital's rule, I'll differentiate the function that's in the numerator and the function that's in the denominator, and then find the limit of the quotient of those functions. So this would equal the limit as x goes to infinity of the derivative of the function in the numerator would be 12x minus 7, divided by the derivative of the function in the denominator is 4x. And now by analyzing the highest degree term in the numerator and denominator, I can see that as x goes to infinity, both the numerator and denominator are going to infinity. So that gives indeterminate form of type infinity over infinity, which means we can apply L'Hopital's rule again. So I'll differentiate the function in the numerator and the function in the denominator, and then try evaluating the limit again. So this would be the limit as x goes to infinity of the derivative of 12x minus 7 is 12, and the derivative of 4x is 4. And that's just a constant value, so I know this limit is equal to 3. Must know number 8, other indeterminate forms. In this section, I want to show you a couple tricks for how to evaluate an indeterminate product of type 0 times infinity and an indeterminate difference of type infinity minus infinity. Now, in the last section, you learned a rule called L'Hopital's rule, which says that the limit of a quotient of functions is equal to the limit of the quotient of their derivatives. But an important part of L'Hopital's rule is that it can only be used when, if you were to evaluate f at c over g at c, you got indeterminate form of 0 over 0 or infinity over infinity. So with either of these indeterminate forms, you can't use L'Hopital's rule, unless you use a trick to rewrite them so they turn out to be in one of those indeterminate forms. And that's what we're going to do. So let's start with the indeterminate product. I want to find the limit of x times the natural logarithm of x as x approaches 0 from the right side of 0. As x approaches 0 from the right, x would be approaching 0, and the natural logarithm of x, if you remember what its graph looks like, it would be approaching negative infinity. This is an indeterminate product. It doesn't tell me what the value of the limit is, and it doesn't even tell me if the limit exists or not. So what we can do, if I erase this, is we can rewrite this product of functions as a quotient of functions, and that's going to end up giving me this indeterminate form of type infinity over infinity so that I can use L'Hopital's rule. So let me write them as a quotient. I'll leave the natural logarithm of x in the numerator, and then in the denominator, I'll write the reciprocal of x. Notice that dividing by 1 over x would be equivalent to multiplying by x, as long as x isn't equal to 0. And that's fine because we're just finding the limit as x is approaching 0, which means x is never actually equal to 0. And then if I were to try and evaluate this limit, as x approaches 0 from the right, the natural logarithm of x goes to negative infinity, and 1 over x, as this denominator gets infinitely small, this fraction gets infinitely large, so it would go towards infinity, which means this would be negative infinity over infinity. When you have this indeterminate form, that's a format where you're allowed to use L'Hopital's rule. So I know this limit would be equal to the limit of the derivative of the numerator divided by the derivative of the denominator. And the derivative of the natural logarithm of x is 1 over x, and the derivative of 1 over x is negative 1 over x squared. And then simplifying this using exponent rules, I know it would simplify to just the limit as x approaches 0 from the right of negative x. And that would just be equal to 0. Now let's try and evaluate a limit that results in an indeterminate difference. If I tried to evaluate the limit of this function as x approaches 0 from the right, both sine x and x would be approaching 0, which means both of these fractions would be approaching infinity. So I would have indeterminate form of type infinity minus infinity. That doesn't tell me the value of the limit, and I don't even know if the limit exists from that answer. So I'll erase that, and I will try and get this expression into a format where I get indeterminate form of type 0 over 0. And that would happen if I combined these into a single fraction by getting a common denominator. So I'll multiply this fraction top and bottom by x, and this one top and bottom by sine x. And that allows me to write the difference of those terms as a single fraction. Now if I tried to evaluate the limit of this function as x approached 0 from the right, I would get 0 over 0. When getting that indeterminate form, we can now use L'Hopital's rule. So I know this would be equal to the limit as x approaches 0 from the right of the derivative of the numerator divided by the derivative of the denominator. So I'll write those derivatives. And then when evaluating the limit of this function as x approaches 0 from the right, I would have 1 minus 1 over 0 plus 0, which is just, once again, indeterminate form of type 0 over 0. So I can apply L'Hopital's rule again. It would equal the limit as x approaches 0 from the right of the derivative of the numerator divided by the derivative of the denominator. And I'll fill those derivatives in here. And then when evaluating the limit of this function as x approaches 0 from the right, that term goes to 0, but these cos x's would be approaching 1. So I would have 0 over 1 plus 1 minus 0. That's 0 over 2, which is just equal to 0. Must know number 9, the squeeze theorem. This theorem is sometimes also called the sandwich theorem. Let me start by defining the squeeze theorem for you. Let me draw a graph of a couple functions. Let's say we have some function h of x and some other function f of x. If there is a third function, let's call it g of x, that is always between or equal to these f and h functions, and the limits of the h and f functions as their x values both approach an x value of, let's say, a, and I'll label it here. If the limits of both of those functions as x approaches a, if they're both equal to L, and g of x is always between or equal to f and h of x, we know that g of x will be squeezed between h and f of x so that it has the exact same limit as x approaches a. And let me formally write that for you. So if g of x is always between or equal to f and h of x, when x is near a, and except actually at a, we don't care what actually happens exactly at a, and also if the limit of both the f and h functions as x approaches a is equal to L, then that means this g of x function, which is stuck between the h and f of x function, as its x value also approaches a, its y value would have to be approaching L as well. So those 3 bullet points are the 3 conditions of the squeeze theorem. And now let me make a little bit of room and let's do an example where we can use it. Let's try and find the limit of this function as x approaches 0. Now as x approaches 0, x squared approaches 0, but sine of 1 over x as x approaches 0, that function actually oscillates wildly as x approaches 0. So the limit of that function doesn't exist as x approaches 0. But we are actually able to find the limit of this product if we use the squeeze theorem. And how I would do that is I would start by looking at the sine of 1 over x function. Well, sine of any argument is always going to be some value between negative 1 and 1 inclusive, which means sine of 1 over x is always going to be greater than or equal to negative 1, but less than or equal to 1. But this function in the middle, I actually want it to be x squared times sine of 1 over x. So let me multiply all 3 parts of this inequality by x squared. And now I can see that this x squared times sine of 1 over x function is always between those 2 functions. And I know what those functions look like. And now I don't know exactly what this function looks like, but I know it's always between these two functions. So it's going to look something like this. And because this function is always between these two quadratics, I know that if these two quadratics share a limit as x approaches 0, then this function, which is squeezed between them, has to share that same limit as x approaches 0. Right? The limit as x approaches 0 of the negative x squared function, as x approaches 0 from both the left and from the right, the y value seems to be approaching 0. And then if we look at the positive x squared function, as x approaches 0 from the left and from the right, it's approaching this point here, which has a y value of 0 as well. So since both of those functions share the same limit, we've now met the first two criteria of the squeeze theorem, which means the third statement here must be true. It means the function between x squared and negative x squared must share that same limit. As x approaches 0, this function must also be approaching 0. So we can state that as our final answer. Must know number 10, the epsilon delta definition of a limit. So let me draw a diagram that we'll reference throughout its definition. Let's say we have some function f at x, and we're finding the limit of this function as x approaches some value, let's call it a. And then let me show in the diagram where the limit of this f at x function would be as x approaches a. It would be at this value L. And based on the formal definition of a limit, it says that L is the limit of f at x as x approaches a if, for every epsilon greater than 0, there exists a delta greater than 0 such that if the magnitude of x minus a is bigger than 0, but less than delta, then the magnitude of f at x minus L would be less than epsilon. Now this might look complicated, but what it's saying is that the limit of this function as x approaches a is L if, for any non-zero distance, I move above and below L from, and we call that distance epsilon. So notice I've moved 1 epsilon above the limit, so the limit plus epsilon, and 1 epsilon below the limit, so I'll call this the limit minus epsilon. So for any epsilon bigger than 0, wouldn't matter how big or small epsilon was, I should be able to find an interval of x values that would guaranteed find me a function value within that range. And let me extend these lines so you can see what I mean. So for this to be the limit of the function as x approaches a, there has to be some value delta, which creates an interval of x values. Let me move a distance of delta to the right and to the left of a, so that as long as I pick an x value within that interval, so pick any x value in this interval, I would guaranteed find a y value on this function that is within this interval. So for example, let's say I picked an x value right here. At that x value, I see the function is here, and the y value of the function at that point is right here. So notice, as long as I pick an x value that is within delta of a, up to 1 delta bigger than a, or 1 delta less than a, then I know the y value will be within 1 epsilon of the limit. And if we look back over to here, the magnitude of x minus a, we're going to interpret that as just the distance from x to a. And if I zoom in on the diagram, that distance from x to a would be this section right here. If that distance is bigger than 0, but less than delta, meaning we pick an x value somewhere within this interval, then we know for sure that the distance between f at x and L, which if I look at the diagram, would be this distance right here, we know that's going to be less than epsilon, meaning that the y value is going to be within epsilon of the limit. So no matter how big or small we set that epsilon, as long as there is some value of delta, that as long as we choose an x value within delta of a, and we're able to get a y value within epsilon of L, then we know that L is the limit of f at x as x approaches a. And I'll write out that abbreviated version of this rule below the graph. So there you go. Hopefully if you watched all 10 sections of this video, you have a better understanding of limits, and let me know what you want a top 10 of next. Jensen Math!